Hello, differential equation students. Today we are doing a just brief overview of some content from chapter 10. We're going to be very superficial. I only have 3 slides to discuss here. But chapter 10 deals with coping with nonlinear, autonomous, planar systems and other higher dimensional systems too, but we're only going to focus on planar, meaning 2-dimensional. And we want the systems to be autonomous. If you recall, that means that the derivatives are only expressed in terms of constants and the functions themselves. So you never see the independent variable, say t, in the differential equations. So no t's visible, no explicit t's visible. And then nonlinear. So this takes us away from all those methods that we've been learning using matrices and eigenvalues and eigenvectors. Typically, nonlinear systems are not solvable by hand. So the approach will be to, and when solving them, is to approximate solutions to do what's called linearization of the system to approximate solutions. But here we're only going to focus on analyzing phase portraits, and that will be all that we do for this chapter. Okay, let's do some definitions. Given any planar autonomous system of differential equations, the x nullclines are all points in the xy plane at which x prime is 0. And the y nullclines are all points in the xy plane at which y prime is 0. All points of intersection of these two sets, of these two nullclines, are called equilibrium points. So consider the system below. It's nonlinear. We know it's nonlinear because we have, here's a nonlinear term right here. We have an x times y. That makes it nonlinear overall, and both equations have a nonlinear term. We just needed one equation to have a nonlinear term to be a nonlinear system. And notice it's autonomous. There's no t's explicitly involved in the system. And this is a model of a predator-prey relationship where x will be the population of the prey in thousands and y will stand for the population of the prey of the predators in hundreds. We're going to find the nullclines and the equilibrium points, and we're going to analyze the behavior of solutions along the nullclines, and then we'll confirm our analysis by creating a phase plane portrait of possible solutions using technology. All right, so the work we do by hand. Let's first begin by finding the x nullclines. That's simply done by setting x equal to 0 and finding all points where that happens. So we say 0 is equal to x prime. Do some factoring. Be careful you don't divide by variables, like don't divide everything by x to get rid of it. You lose solutions when you do that, so factor x out instead. And that leaves a 4 minus 2y. All right, I can see two different solutions here. X could be 0 or y could be 2. Now I'm going to make the x nullclines be one color. Let's make them be red. And then the y nullclines will make them be, I don't know, green. In this picture over here, though, if I wanted to graph the nullclines, x equals 0, you'll notice I have given a space here where we only have x and y as being positive, right? X is over here. X stands for the population of the prey, and y was the population of the predators. And they have different units of measure. X was in thousands, y was in hundreds. And if I were to graph x equals 0, that's just this, it's the y-axis essentially. So x equals 0 is a part of our x nullcline, and then y equals 2 is another part. Now it's both of these parts. All of these points along the red vertical or the red horizontal line are points that are said to be in the x nullcline. Now let's do the y nullcline. Let me make that a little bit smaller over there. Okay, we're going to set y prime equal to 0 and figure out what points make that true. So 0 equals y prime. So So we have negative 12y plus 2xy. Again, I'll do some factoring. I see a y can factor out. I could also pull out a negative 2 if I wanted, but it doesn't really matter. I'll go ahead and do it this time. So negative 2 times y will be factored out. And then that leaves a positive 6 minus an x. So the two solutions I see here are y equals 0 and x equals 6. These are called the y nullclines. They contribute to the y nullcline. So x equals 6 is here. Let's go back to a little bit thicker marker there. Okay, here we go. X equals 6 is part of the y nullcline. And y equals 0, so the x-axis. All right, now the equilibrium points are the points of intersection of the two nullclines. So in other words, where green and red intersect, not where green and green intersect, right? So don't be tricked into thinking, for example, that this is going to be an equilibrium point. It's only where green and red intersect, so where x nullcline intersects a y nullcline. So the equilibrium points, there's only two of them. There's one here at 6, 2, and then there's another one at the origin. Now, equilibrium points are simply points where both derivatives are 0, right? If you plug in the point 6, 2 into this system of equations, plug in 6 for x and 2 for y, you will get 0 for x prime and a 0 for y prime. Meaning that if the populations are 6,000 prey and 200 predators, that's like considered the perfect balance. There's not going to be, according to this model, right? There's not going to be expected changes in population. They sort of struck they found a balance. But if your populations are out of balance, then the differential equation will model how those populations change over time. Like if you have too many predators and not enough prey, we expect, maybe the population of predators or prey will decline, but eventually we're going to get to the point where if there's too little prey, then predators die off, and then when predators die off, the prey will regrow, and then that will support more predators, and you sort of get this cycle of back and forth between the populations of predators and preys. Anyway, the next part, so we found the nullclines and we found the equilibrium points. The 0, 0 is an obvious equilibrium point, right? If there are no predators or prey, we don't expect those populations to change. And now we're going to analyze the behavior of the solutions along the nullclines. Let's focus on x equals 6. And what you do is you let x be 6 and you plug it into this system and figure out what you get for x prime and y prime. If x is 6, though, then y prime is going to 0 out. What that means is that we have, if x is 6, then y prime is 0. Let's do a 6 analysis. Let me make a little bit of space here, put my work here for the two nullclines. Now, I'll show my thinking here for when x is 6. We have that x prime will be equal to, just plug in a 6 for all the x's and rewrite this. So we have 24 minus 12y. And we have y prime is equal to 0. Because 6 is part of the y nullcline. Okay, now what this is telling us is that pick any point, along x equals 6. Let's focus on a point like at 6, 1. Let's put a point right there. And let's do these next points in a different color. How about blue? So we're going to focus at the point here, 6, 1. Now, since every point along x equals 6, y prime is 0, we expect no vertical movement of the solution. Right? You would not expect the solution to try to be going up from that point because y prime is 0. And if y prime is 0, then the change in y is not happening. In other words, there is no vertical change, only horizontal change is happening along this nullcline. In particular, if we stay below, so that an arrow pointing up is not possible for the direction of the solution. This is going to have to only point, right or left. As time goes on, the solution is going to have to go left or right from there. It can't go up because y prime is 0. But if you plug in 6, 1 now, like plug in a 1 for the y, you're going to get an x prime of 12. Well, that's positive. That's suggesting that the solution through this point is trying to head this direction, if x prime is positive. And if x prime is positive and large, you can just make like a larger arrow or something like that. So you can use length of arrow to indicate how quickly of a direction, or how quickly we expect the solution to be changing. But let's not worry so much about getting our lengths all correct. But we just have x prime is going to be positive, right? When I plug in the point 6, 1, especially y, plug in y equals 1 to this x prime, you get 12. So we have a positive change, or x is increasing because x prime is positive. Okay, now the closer I pick points to this solution, to this equilibrium point, like plug in a higher value, but not quite 2, like 1.5. I do 1.5y, so you're going to get a smaller x prime. In fact, x prime will get closer and closer to 0 the closer up we get to that equilibrium point. And so what we could do then is reflect an understanding of that by doing, and also I should say, the closer we get to the 0, as y gets closer to 0, as that gets close to 0, then we have x prime being very large. So we have a rather large rate of change going this way. And then as you go up, they'll get smaller and smaller. Okay. But we expect the solutions to be moving left to right at different speeds depending on which point of that we're looking at. If I analyze above the equilibrium point, like start plugging in y coordinates that are more than 2, like 2.5 and then 3 and 4, etc. If we try to plug in 2, we're going to get x prime equals 0. So there's going to be no movement at all at that equilibrium point. But as soon as you go above this, you're going to start getting negative numbers. And the farther up you go, the more negative we get. And so this suggests we have movement going left. And the further up we go, we get more and more rapid movement to the left along this nullcline. Okay, let's focus on a different nullcline. Let's do the y equals 2 portion of the x nullcline. Let me give myself a little bit more space here to analyze some of these things. Okay, y equals 2. If y equals 2, plug 2 into both equations up here, and we're going to get x prime is 0, because y equals 2 is part of the x nullcline. And we'll get y prime equals, plug in y equals 2, we get negative 24 plus 4x. Just plugged in y equals 2 into that. And now we want to analyze, different points along this horizontal red line here. Like what happens if I go to the right of the equilibrium point? Plug in a point, say 7, 2. So x will be 7. Or if you plug in a 7 there, you're going to get 28 minus 24. You're going to get a positive y prime. And the bigger x you pick, the larger y prime will be. Excuse me. And so we're going to get solutions that go up, positive y primes, and the further out you go, the more quickly the populations will be climbing. Or at least the y population will be climbing. The solution will be climbing faster, I'll say that. And if you pick x coordinates left of 6, like start with 5, right, plug in a 5 there, you're going to get a negative 4y prime. And the further away from x equals 6 we get to the left, the more negative y prime will become. So we get the y's are dropping, and then further you go this way, they drop more and more rapidly, kind of thing. All right, let's analyze next what happens along the axes, the other parts of our nullclines. Let's start with the vertical one, x equals 0. So along x equals 0 is part of our x nullcline. So x equals 0 will give us an x prime of 0, which means we expect no left-right movement along this nullcline, or at least along this portion of the nullcline. But we'll see what happens to y prime in a second. So if x prime will be 0 and y prime will be, plug in 0 for x, we just get negative 12y. Okay? I just plugged in x equals 0 right there. Okay. X is negative 12y. So this is suggesting now pick different y coordinates along here. Right? Pick a point like at 0, 1, for example. So plug in y equals 1, and we expect to see some dropping. In fact, the further up we go along this line, we get a more negative y prime. So we get some small y primes here at the start. And just to avoid, let me put the arrows just to the left of it so we can see. So we have going down, but then going down more, and the further up we go, right, the more quickly the population is dropping. This is suggesting that if x is 0, remember x is the prey population. If the prey population is 0, and you start with a non-zero predator population, you can expect that predator population is going to decline rapidly to 0 as well. If they have no food, their population will go to 0. So if the predator population starts way up here at 6 and there's 0 prey, you expect rapid decline to happen. Okay, in the last portion of the y nullcline, which is the horizontal line, y equals 0. So along y equals 0. And I'm just analyzing these in no particular order here. Maybe I could structure this better in post-production, but we have y equals 0. Along this nullcline, or this part of the y equals 0 is a green horizontal line. This is part of our y nullcline. So we know that y prime will be 0 when y is 0, but what's x prime? X prime is going to be 4x when y is 0, and y prime will be 0. Okay, so we expect no vertical movement because y prime is 0 along this portion of the nullcline, but we expect lateral movement because x prime is non-zero. If you pick a point like when x is 1 and y is 0, so focusing on that point right there, plug in 1 for x, you get x prime is 4. And the larger x gets, the bigger x prime becomes. Right, so we expect small little arrows going off to the right at the start, and they just get longer and longer and longer as we head off this way. This is suggesting that if you start with a non-zero prey population and there's 0 predators, that you can expect that prey population to just grow exponentially out of control. Now, of course, there are other factors to consider, but this is a very simple model. All right, there's our analysis. We found the nullclines, we found the equilibrium points, and next we will go to use technology to make phase plane portraits. All right, so go to Google and type in D-field and P-plane and do a search, and open up this one here. This is Java versions, if you haven't done this already. And for the P-planes, go down here to pplane.jar and download that. Now you may also have to get some Java installed on your machine so that this will run. There's a link for that down here. When you do get this downloaded, you should see this field here with the Java icon that shows that you have compatible software. and then go ahead and open that. Okay, let's get rid of that. Let's get rid of that. Let's move this up here, make this a little bit bigger. And let's open up a window that says solution, input, keyboard input of initial value. Let's get that open as well and bring that down here. Okay, our first example is this x prime equals 4x. Let's delete the example I have in there. 4x minus 2xy is x prime, and then change out y prime. Y prime was negative 12y plus 2xy. And then say, oh, you can change our window too. Let's do, since we're only really interested in the when x and y are positive for this one, this is the predator-prey, let's just do a window that goes from -1 up to, say, 10, and then y will be -1 up till 10 as well. Let's say graph phase plane. All right, here we go. Here's our phase plane. This software also uses length of arrow to indicate speed at which the solution is changing and also which direction it's going. Length to indicate speed, and obviously the arrow to indicate direction. You can see a bunch of spiraling circles. The equilibrium point is at 6,2, so it's right here. This is the perfect balance between population of prey and population of predators. Remember that y was predators in terms of hundreds and x was prey in terms of thousands. So like the perfect balance for this particular relationship is 6,000 prey to 200 predators. If those numbers get out of that, away from that equilibrium, then you have the populations will change according to this model. And you click anywhere in here. Let's pick a point, or you can pick an initial value by entering it as well. Let's say that we have, I don't know, 5,000 prey, and we have 300 predators. And then say solve, and notice the solution it produced. So we started at this point right here, and because we had too few prey and too many predators, we had both quantities going down. Like the predators were eating that prey all those predators were eating the too low amount of prey, and they were eating them all. But predators there wasn't enough to sustain all those predators, so both quantities are decreasing to a point where the predator or the prey population is decreased and the predator population is decreased to the point where the predators start to rebound. The predators continue to decrease while the prey rebounds, and the prey is getting bigger and bigger, and eventually the prey gets to a point where it sustains those predators, and we get more and more predators. And more predators and more prey, it starts getting to the point where, okay, now we have too many predators, we're starting to reduce the number of prey again while the predators keep going up, and we enter this cycle. The populations kind of go back and forth, and then you just click anywhere else in here and you get different cycles. If you click close to the equilibrium, we get much smaller cycles of the numbers. And then of course if we picked, let me pick a solution where we have 0 prey but 300 predators and say solve. Right. Time going 0, by the way, time 0 is right there, and as time went on, the solution went down this way. Negative times, the solution went that way, but we're just interested in positive times. Anyway, the solution went just down to 0. If there's 0 prey, then of course you expect the predators to diminish to nothing as well. Or you can pick a point somewhere along the x-axis. So say we have 2,000 prey but no predators, and say solve. Right, that was our initial point right there, and as time went on, the number of prey just went off to infinity, assuming no other factors taken into account. This is a very simple model. But juxtapose this or overlap this with our analysis in our other picture, and you see that our analysis was able to predict the motion, at least the counterclockwise rotation of the solutions around the equilibrium point. Okay, in this example right here, let's find the x nullclines first. So we set x prime equal to 0 and solve. I get two answers to this, x equals plus or minus 2. And now let's do the y nullclines. Set y prime equal to 0. And do some factoring. I can factor out a y, so let me just go to write this in factored form. And that leaves a 2y plus x. So this gives us y equals 0. And also the other one doesn't give us a vertical or horizontal line, but it gives us a relationship. Y equals, set that equal to 0 and solve for y, you get y equals negative x halves. Okay. So let's plot these in our space over here. X equals plus or minus 2, so we have a vertical line here and a vertical line over here. And for the y nullcline, we have y equals 0, which is across here, and y equals negative x halves, which is this diagonal line here. Okay, that looks good. Now keep in mind, we're only looking for the equilibrium points are intersection of green and red, not every intersection that you see here. That's why the different colors are helpful. So let's identify those next. Green and red intersect at this location, over here, and right here. Okay, now let's analyze along some of these nullclines. Let's do the analyze along the red x nullcline first. I'm going to go color-coded here. Let's focus first on x equals negative 2. When x equals negative 2, we get x prime is equal to 0, but y prime is equal to 2y squared minus 2y, which factors. Right, we can factor out a 2y, leaving y minus 1. This is important to factor this because we're going to see that at different points along this vertical line, we have y prime having different signs. So if we're above this equilibrium point, go above that one. So plug in y coordinates that are more than 1, like 2, for example. Right? Plug in 2 for the y's. And what sign for y prime do we get? We get a positive. In fact, the further we go up, the more positive it becomes. So we have solutions that are getting away from that equilibrium point if you pick y coordinates that are more than 1. If you pick y coordinates between 0 and 1, for example, a half, plug in a half into those statements and you're going to get negative numbers. And it'll get more and more negative as you get towards 1 half itself. That's where this will be the most negative. Or as I'm thinking of what the graph of 2y times y minus 1 looks like. It's a parabola opening up at 0 and 1. It looks something like this. And so if y prime is a function of y like it is here, then at 1 half, we have y priming as low as possible. So we get the most decrease right there at the middle, and then we get a little bit of decrease right as we approach that other. So it slows down as it approaches that equilibrium. Okay, now let's analyze on the other side. If y is negative, if I plug in like negative 1, for example, we're going to get positive y primes. So positive y primes will be low and positive as you're close to it, and they get more and more positive as you go down, so you get more rapid ascent. So if you might remember when we did one-dimensional analysis, and it looks like we have something that looks kind of like a unstable equilibrium point, at least along this vertical line, and here we have a stable one, at least along this line. Solutions go away from one and approach the other. And let's do the other vertical line. X equals 2. Okay, so this is part of our x nullcline, so we do expect x prime to be 0, which is true, right? Just plug in 2 up here. Plug 2 into this statement, you get 2y squared plus 2y for y prime. Factor out a 2y. Okay. So revealing two different equilibriums along that 0, -1, which we already knew, right? Y equals 0, y equals -1 are equilibriums. The question is, what do the solutions do if you're in between these? Like plug in a -1/2 for y. If you plug in -1/2 for y, you're going to wind up getting a negative result. So we expect the graph will head down and get down more rapid there, and then we'll be heading down. If you go above, like plug in y coordinates that are above 0, then you're going to get y primes that are also above 0, positive, which means that y is going up. And it'll be going up, more and more rapidly, right, as we go along that vertical line. And how about below -1? We expect solutions to also be going up, right? If you plug in like -2, right, for these y coordinates, you're going to get a positive y prime. So we expect solutions to be going up. So again, it looks like we have something similar to an unstable equilibrium versus a stable equilibrium along that vertical line. And now let's analyze along the y nullclines. Let's start with the y equals 0. If y equals 0, x prime is going to be, plug in 0 for y. We get x prime is not affected by that choice of y. It's still just 4 minus x squared, which is 2 minus x times 2 plus x. And y prime is 0. So along the y nullclines, we expect no vertical movement, just horizontal movement. So all of our little arrows should be left and right only. The question is, should it be left or right? And that'll depend on, the coordinates we pick. So if I'm going to focus on this portion right here, pick an x coordinate that's less than -2, then we get negative results. Like plug in -3 and -3 here and here. We'll get negative results. And they'll become more and more negative. So we expect the x's to be going left. And they will go more and more left as you head that way. Now let's focus on in between, what the solutions are doing here. If you pick any x between -2 and 2, such as 0, for example, you're going to get positive values. So x prime will be positive, meaning x will be increasing. And so it'll increase a little bit when you're close to the equilibriums, and it'll increase most rapidly here towards the middle, but then it'll slow down its pace as you approach the other one. Right, because x prime, if you were to make a graph of an x prime against x, it would be an upside down parabola like this. Right, positive in between. X prime is positive in between the intercepts, therefore x is increasing, and it's most positive here in the middle, so it's increasing most right at the middle, which is why I was saying that in my analysis. And then let's do our last last portion of our y nullcline. That was when y is equal to -x halves. Well, there are no, again, there are no y's here to plug into. So x prime is still governed by just 2 minus x times 2 plus x. And y prime is again 0. But if you pick, it's going to be entirely dependent on what x you pick will determine what x prime is. And if you pick x prime, or x's that are left of -2, we're essentially going to get the same arrows that we see right there. We'll get those exact same arrows, but they're going to be along solutions that go through this portion of our y nullcline. So get more and more negative as you go that way along that nullcline. They're going to go more and more positive this way, being longest in the middle, and then they'll start to shrink in size again. Oh, we didn't finish our analysis over on this side. We forgot to do that part. I forgot to do that part. If you plug in numbers, let's go back to this nullcline part of the nullcline. If you plug in numbers that are more than 2 for x, you're going to get negative results. And they'll get more and more negative as you go further and further to the right. So we'll get, small negative, go away. Small negative, close to equilibrium, and then more and more negative as we go further away. Same thing's going to happen along this diagonal portion of the nullcline. All right, next, so we've analyzed the solutions as they interact with the nullclines. Now we're going to go to the phase plane portrait and do this there. Okay, the next one, let's go up to here and change our differential equation. We had 4 minus x squared was the x prime, and the y prime was 2y squared. Oops, that's not a y. 2y squared. There we go, plus xy. Say graph phase plane. And let's change our window now to include, let's try to roughly match the window that was in our notes here. So I'm just going to do -4 to 4, -4 to 4. Now I'll say graph phase plane. All right. We had solutions in this one here that we had equilibrium at -2, +1. But we saw an instability at that equilibrium point. So solutions will go away from it in different directions. We had an equilibrium point down here at -2, 0. That it had more of the appearance of a saddle, right? Some solutions will ride up to that or ride down to it, and other ones will approach it but then go away from it. We'll see that here in a moment. And we had another equilibrium that was kind of like a saddle over here at 2, 0, and then an equilibrium that was like a sink and not a source, right? The one up here, -2, 1 was like a source. Solutions went away from it. Here, at 2, -1, they sink towards it. And then you start clicking in different places. Right? So notice the solution here curved around, sort of bending away from the saddle that was here at -2, 0. But then it gets closer and closer to the sink and approaches that sink. You can do several such solutions in this region. They all approach that sink. If I go, let's go in the little triangle portion here and see what the solutions do. Ignore this part of our solution. This is our starting point. So it went off this way, and then it went off following a vertical asymptote up. Click on several. Notice how these solutions, they go away. Notice how these solutions go away from the source. Oh my goodness. I've got to turn these notifications off. They drive me crazy. They go away, go away, go away from this equilibrium point. We have an equilibrium point right here, but it's like a saddle. And the only way a solution will go to that is if it starts there. All other solutions around this will go away from it in a saddle-like manner, like we analyzed with our linear planar autonomous equations. And then, let's do some more around this sink. And then some more around this saddle. All right, you get the idea. And then over here is get some in this quadrant just so it doesn't feel left out. When you start seeing all these different possible solutions, you see this one is like this will be a nodal source. The equilibrium solution here is a saddle, another saddle there, and a nodal sink here. And compare this against the analysis we did using the Nullclines. All right, on this last one, it's a good time to pause the video and you try this by yourself, and then you can watch the video to see if you've got a hang of it. And this would be good enough for your practice, in my opinion. If you need more practice, just start from scratch with all three of these and try to do them yourself and make sense of what you're doing. All right, let's start with the x nullcline. So we're going to say x prime is 0. We're going to do some factoring on that x prime. So I get two answers here, 0, x equals 0 and y equals 1. And now let's do the y nullcline. So 0 equals, here there is no factoring that can be done. This is the best we can say is right here, which means that y equals x squared is going to be our y nullcline. Okay, and now we're going to graph these things over here. So y equals x squared is just your basic parabola. So we have a parabolic nullcline, which is just fine. And then we have, over here, the red ones, we have x equals 0, y equals 1. Okay, now we're just looking for the points of intersection of red and green. Those will be our equilibrium points. So there's one here at negative 1, 1, one here at 1, 1, and one down here at the origin. Now let's analyze behavior along the x nullcline, each portion of it. Let's start with x equals 0. Plug in 0 to the differential equations, and you get x prime is 0, which isn't surprising since that's part of our x nullcline, and y prime is equal to negative y. So whatever y is, change its sign, and that's going to be what y prime is. So if y is negative and small, then y prime will be positive and small, so y will be increasing. So if we're down here, y will be increasing, but not much, and the further down you go, y will increase more and more towards that equilibrium. Whereas if you go above, it'll decrease a little bit at first, and then more and more rapidly the higher up you go. It'll decrease down towards that equilibrium. Let's do the next one is at y equals 1. Plug in y equals 1 into the differential equations. We're going to get x prime is going to be 0. That's not surprising because y equals 1 is part of the x nullcline. And then plug in y equals 1 into the other equation. We get y prime is equal to x squared minus 1. Which we could factor x minus 1 times x plus 1. Okay, along the red horizontal line, again, we only expect vertical movement because y prime is non-zero, but x prime is 0. So no horizontal movement anywhere along that horizontal red line. And knowing what the graph, if I were to graph this y prime against x squared minus 1 looks like this parabola. So I know that we have y prime will be positive if I'm left of negative 1 and positive if I'm right of positive 1. And the more and more positive as you go further and further away from those points, right? Because this gets more and more positive. So positive, but not much, close. And then as we go further and further, it gets more and more positive. Right? Positive, but not much if you're close, and then more and more positive as you go further away. Now in between, we see that y prime is negative, but not much negative, and then more and more negative, and then the most negative right here in the middle, and then less and less negative again as we get towards that one. And now we're going to analyze what happens along y equals x squared. If y is equal to x squared, then x prime is equal to x minus x cubed, which can be factored to x times 1 minus x squared, which can be factored to x times 1 minus x times 1 plus x. And y prime will be 0. In fact, let me put y prime equals 0 above. So no vertical movement along this green parabola, only horizontal movement, and that horizontal movement is dictated by this cubic function that we have here. All right, if you were to graph this, x prime against x, you would see 3 intercepts. You would see this kind of graph if you were to graph this function here. So x prime is positive if I'm looking over here, it's positive and positive. It's positive left of -1 and positive between 0 and +1. So let's focus on the left of -1 first. It gets more and more positive, and this is x prime. So it's we're talking left-right movement, and positive means to the right. So it's a little bit to the right, more to the right, even more to the right, even more to the right, etc. as you go along that nullcline, portion of the nullcline. Between 0 and 1, x primes are negative, and they get most negative at some point in between 0 and 1, but then they get back towards 0. So we have a little bit of negative, a little bit more negative. At some point there's going to be the most negative, and then it'll get a little less and less negative. Between 0 and 1, it does just the reverse, but to the right, because x primes are positive. So a little bit to the right, a little bit more to the right. At some point it's going to be the most to the right, and then it's going to slow down again to the right. And then finally, along that last portion, right, focusing where x primes will be negative, but more increasingly so. So more and more to the left is what we expect the solutions to do. All right, so the final step here would be, now let's do a phase plane portrait and analyze this and confirm our analysis. Okay, and then the last one. X minus xy was our x prime, and our y prime was x squared minus y. Let's keep this same window and say graph phase plane. All right. At first glance, it looks like I'm seeing like a heart. Well, we had 3 different equilibrium points. They were at -1, 1. So there's an equilibrium point right in this area. There's an equilibrium point at 1, 1, 1, which is here. So -1, 1 there, and 1, 1 here. And then at 0, 0. If you look at the arrow, 0, 0 is a saddle. It appears to have the appearance of a saddle. If you were to, let's pick a point that's on the nullcline x equals 0. So let's say that x equals 0 and y equals -5 to start, and say solve. Notice that solution, it started off the image, but it approached the equilibrium point and sunk into it, if you will, approached it. If we start above, like at +5, and say solve, we have a solution going the other way. It starts up here and just sinks right down to that equilibrium point. However, if you're off that nullcline by just a little bit, like -1, let's see what happens here. Okay, this is interesting. So we have a solution that was approaching the equilibrium solution here, but then it bends away, and then it winds up actually sinking into this equilibrium here. So this reminds me of a spiral sink. Right, if you pick any solutions along here, all solutions on the left side of the y-axis all will spiral towards that solution, this spiral sink. If you pick solutions to the right side of the y-axis, they also are spiraling towards that sink. So we have a spiral sink at this solution. No solution will approach the 0, 0 unless that solution starts on the y-axis. So if you start on the y-axis, there will be no left-right movement. It'll only have vertical movement down to this will be a sink as well, and a sink as well. At least it sinks along this direction, but they repel in the other direction. So this is more like a saddle here, a saddle, and then a spiral sink and a spiral sink.